Much as I would love to continue talking about AI and all the fun stuff and the world being over, that'd be great. I'd love to. Love to. Uh, but we got more important things to talk about, right? This stuff right here, way more important. So, we talked about last time. I want to do one more example. So hopefully you guys are able to do this one. Really? I haven't even started. I haven't even started in this and it's been broken. I want to do one more example of synthetic division just to kind of drive the point home. Especially, I forget who asked it last time, but was wondering about the fact that the leading term on all of my examples was always a leading term of one on our dividend, the thing that's being divided. So I wanted to create another example. And so that's what we're going to do. Let's add an extra page. So let's go ahead. Um, Example, divide. Let's do, someone give me some numbers.
Three.
Negative 2x to the fourth minus 23x squared plus 8x minus 9 divided by x plus what number? 7. I was hoping someone would say 7. Okay. So, what is our C value in terms of the synthetic division? Is it positive 7 or is it negative 7? It's negative 7 because remember, we need the thing to be in the form x minus C. So our C value is negative 7. And then we set up the synthetic division, and we can do synthetic division here because we're dividing by x minus c. 1x minus a number. If it was x squared or if it's 5x, we would not be able to use it. And we're going to know why this is useful for us in just a moment. So negative 7 divided into negative 2x to the fourth. Then notice that there is no x cubed term.
So you're gonna have to add to make a number of like 0.
Yes, so we're going to add a placeholder. So we're going to add a plus 0x cubed. So plus 0x cubed. So we need to make sure we, like, just like with a number, we have to have all the digits. Even if the digit's 0, we have to have it. In the same fashion, every digit, quote unquote, of x needs to be present. So negative 2, 0, negative 23x squared, 8x, and minus 9. And we put the bar right before the constant term because that's where we're going to find our remainder. This is where our remainder is going to be, where I put that circle. So if you remember the trick, the first column, the first entry in the first column always comes directly down. And then after that, it's always multiply diagonally, add vertically. So negative 7 times negative 2 is positive 14. 0 plus 14 is 14. 7 times 14 is 98. I think it's 98, but let's see. No, it's no 96. Let's see. Am I right? 7 times 14. Yeah, 98. So negative 98. And yes, these are going to be big numbers. Like we try not to have them be obnoxiously large numbers, but every once in a while it happens. So make sure you're comfortable with your calculator. It's totally fine to add these things together. That'll be 121, or negative 121, and then negative 7 times 121. Well, negative 7 times negative 121 is 847. And then that's going to be 855. And then times that by 7 is negative 5,929. And add those together, you get negative 5,938. Not very comfortable numbers, but fine enough. Fine enough to work with.
Yeah, they're quite big.
That's okay. Like that can happen. Usually it doesn't get that obnoxious, but this was one where I chose a very, very large divisor, C value, negative 7. And we did a pretty large polynomial, and we also had a very, very large x squared coefficient. So that should really kind of expand things quite a bit. So we've got that. So that gives us our polynomial long division. We had a degree 4 and we divided by a degree 1. So the quotient, the result, should be a degree 3. So it should be negative 2x cubed plus 14x squared minus 121x plus 855 plus a remainder of negative 5,938 divided by x plus 7. And now, while it would not be comfortable to do, it would not be fun, we can, in fact, check our work. If we multiply all these terms by x plus 7, i.e. multiply the whole expression by x plus 7, we can then simplify it, and it should break down back into this, into the dividends. So it's just a nice little nifty trick to check your work if you have time. Eric, yes.
If you ever have a number with that X, would that ever matter?
Which one?
Like, you have X plus 7, say it was 2X plus 7, would that 2 ever matter?
So yes, the thing is, if there was a 2, then we could not use synthetic division. There is a way around it, not like I'm sure this is cool to do. So let's say if instead it was something like 3x squared plus 2x minus 7 divided by 5x minus 2. What you could do to get it into the proper format for synthetic division is you could rewrite this. You could factor out a 5, and then when you factor out a 5 from x, you get just an x. But when you factor out a 5 from 2, you have to write it as negative 2/5. Because we're like, remember, like this is way back when we were talking about how to factor out GCFs. But basically, when you're factoring out a GCF, you're dividing each term by 5. That's what's happening. When you factor it out, you're dividing each term on the inside by 5. So that's why it's 2/5. Then the other thing that you do now is you rewrite this as 1/5 times 3x squared plus 2x minus 7 divided by x minus 2/5. Then you can use synthetic division on the thing inside the parentheses, and then after that's done, multiply it by 1/5. So you can do it. It's just usually it ends up being more complicated than it's worth.
Would you get 1/5?
That's from this 5. In fact, like that's this 5 is this 5. I broke this up into 2 pieces and multiplied by 1/5. Because dividing by 5 is the same thing as multiplying by 1/5.
Yeah.
So now, if anybody does that, I'd be fascinated. I'd be totally jazzed. I've never seen a student do that, but it's definitely an option. Definitely something you could do. So, all right, back to this one. So, why do we care about synthetic division at all? Now, this first theorem is not super useful in its core, but it is useful because it proves the factor theorem. So, if f is a polynomial and it's divided by a function, a binomial x minus c, then the remainder will be f of c. That is, and I can prove it to you very, very quickly, actually, with the division algorithm. If you were to divide by x minus c by the division algorithm, which was right up here, not this format, that's the format we use because that's a very useful applicational format. But if you want to prove something, the bottom format is far more useful. So if you were to divide f by x minus c, then you would have that f of x is equal to q of x, whatever that may be, times x minus c, your divisor, plus your remainder. And because you're dividing by an x minus c, your remainder will always be a number. It won't be a function at all. It'll just be, well, a number is a function, but it'll just be a constant. It won't be anything else. And then if you plug in f of c, that's going to be q of c, which we don't know what that is. We don't know what because this is an arbitrary polynomial. We don't know what q of c would be. It would be some number, but that doesn't matter because it's being multiplied by c minus c, which is 0, plus your remainder. So this goes away and you just have f of c equals your remainder. That's the proof. So that's why I did want to show that just as a nifty little fact. So that's by the division algorithm. So I probably should have written that by division algorithm. You get that. Now, back in the day, back in the old times, in the way, way long ago, when Newton was around and all those people, this was a very, very useful way to figure out values because it allowed us to use like division, a quick division. So imagine this one. If f of x is equal to 2x cubed minus 4x squared plus 5x minus 3, find f of negative 2. Now, we all have calculators. We all have calculators. You can even ask Siri at this point. What is 2 times the quantity negative 2 cubed minus 4 times negative 2 squared plus 5 times negative 2 minus 3? And Siri will be able to calculate for you, or Alexa or Echo, or whatever you want to call it. Any of those things. So the brute force method is probably what we want to use here. Just brute force. So f of negative 2 would just be 2 times negative 2 cubed minus 4 times negative 2 squared plus 5 times negative 2 minus 3. And that should equal negative 45 or positive 45. Negative 45. Negative 45. And because we have a calculator, that's what we should do. That's what we should do. We should utilize our calculators wherever possible. But the olden days, back in my day, when we were really, really excited once we got Barney, it was like there was a big thing about it said live and in purple, right? Because it was a big deal that we got colored on our TVs. Big day for me. I got colored.
Like you're older than you are, but you really aren't.
No, I was born 1960. I'm not really. All right. No. But my parents are very, very old. They do remember TVs before color, which is crazy. Anyways, so the other option would be to the remainder theorem, which is the way technically our textbook wants to solve it, but like it's not valid anymore. But either way, if you're trying to find the remainder, f of negative 2 will be remainder when you divide by x minus negative 2. So negative 2 here divided into 2x cubed minus 4x squared plus 5x minus 3. All powers of x are present and accounted for, so we don't need to put any placeholders. And then go ahead and perform this synthetic division. You're going to be doing it a decent amount in this unit, so make sure you get comfortable with it. So you should get 2, negative 8, 21, and negative 45 in your bottom row. And negative 45 is your remainder. So by the remainder theorem, that is f of c. F of negative 2 in this case. Ta-da! Yes.
Where'd you get the negative 7 from?
The negative 7?
Yeah, I was wondering that too.
Yeah,
The
brute force.
Negative
Negative 7.
Negative 7. Is it 2?
Look at that tail. There's clearly a 2 right there. That is clearly a 2. Fair enough, guys. Thank you. I will make my 2 better. Apology.
A little bit now, but that looks like a 7.
Not anymore.
No, not anymore now.
Be picky. No, I'm kidding. I'm like that was a horrible negative 2.
Pretty sure you were in negative 7.
No. So you can imagine why this would be useful back in the day, because trying to do this calculation without a calculator is a little bit hard to do because you have to keep four different numbers in your head. Imagine if it was even larger, if it was a cubic, a quartic polynomial, degree 4. Or let's say it wasn't -2, maybe it was -10. The nice thing here is it's all it's one calculation at a time. That is the perk of it from back in the day, but now that we have calculators, that's kind of a moot point. However, there is a reason to study it, and it has to do with the factor theorem. If f is a polynomial, then f of c equals 0 if and only if x minus c is a factor of f. So this remember, an if and only if statement means that it's true backwards and forwards. It's a double arrow. It's a double-ended arrow. F of c equals 0 implies that x minus c is a factor. X minus c being a factor implies that f of c is equal to 0. That might seem inherently clear, but it's a very, very important theorem. So what it's telling us at this point is that the zeros make up the factorization of the polynomial. That's what that's telling us. This tells us the zeros / roots form the polynomial. So, oh, that's enough. That's enough there. So here's why the remainder theorem is pretty nice about it, is that if you get 0 for your remainder, that's f of c. So in the remainder theorem, if you get a remainder of 0, you know x minus c is a factor. If you know that you get a remainder of 0, that's f of c. And f of c equaling 0 means that x minus c is a factor. That's what that's saying. It's kind of circular a little bit, absolutely. But let's see it in action. What this tells us, and why this is more useful than the brute force method in certain circumstances, is if you just try, so is x plus 5 a factor of f of x? That's the next question, right? I could plug in -5, right? The factor theorem says that it would be a factor if and only if f of -5 equals 0. So let's, by factor theorem, if x plus 5 is a factor, then f of -5 would equal 0. So if it was a factor, by the factor theorem in the reverse direction, then f of -5. Notice that it's -5 because it says x minus c. So we have to write it as x minus -5 in order to get into the right format. That's why it's f of -5 equaling 0. So we could check by brute force. We could plug in -5 into this and compute it. We have calculators that can compute it for us, and that's fine. That's all dandy. One thing that is problematic there, not problematic, usually speaking, this is step 1 of a bigger problem. The bigger problem would be factor this polynomial. And if we just compute f of -5 in a calculator and get 0, we're going to need to use we're going to need to synthetically divide anyways to find out the factorization. So I'll show you what I mean. Let's use the remainder theorem to check. By the way, I meant to write this underneath it so we remind ourselves this is x minus -5. So our c value equals -5. So you are more than welcome to plug in -5 into the function. If you get 0, it is a factor. If you don't get 0, it's not a factor. But that won't tell you the factorization. That will just tell you that it's a 0. So watch what happens if you use the remainder theorem. So -5, we're synthetically dividing it because we're dividing by x minus c. So 2x to the fourth, so we're just writing the coefficients. So 2x to the fourth plus 12x cubed plus 6x squared minus 5x plus 75. All values of x are present and accounted for, so we don't need to add any placeholders. Go ahead and perform this synthetic division. Yes, JD. Yes, that's correct. Your bottom row should be 2, 2, -4, 15, and 0. And so, because the remainder ends up being f of c, whatever your c value is, and we get 0 for a remainder, that means that f of -5 is equal to 0. And by the factor theorem above, that does mean that x plus 5 is a factor. So the answer to this question is yes.
So it justifies.
Yes. In fact, so here's the reason why we care about the remainder theorem in essence. It's that, in fact, f of x can be rewritten now as x plus 5 times 2x cubed plus 2x squared minus 4x plus 15. Because, I mean, if you think about it in terms of the division algorithm, you divide it by x minus 5, x plus 5. What you get is your function is equal to your quotient times your divisor plus your remainder, but your remainder is 0. So it ends up being that. That's the nifty trick about the remainder theorem, is that if you get 0, then you've already found out what the factorization breaks down into. If you just plug in f of -5 into your calculator and get 0, you're going to have to do this anyways. So that is a nifty thing if you're just asked to check one factor to see whether or not it's a piece of it, or if you know that it's a factor. So, yes, Ben.
Why would finding just one factor be important rather than every factorization?
Excellent question. Why would it be? So Ben is asking, why is it necessary to know what one factor is? Well, as it stands, it was proven by a 19-year-old at one point in the late 16 or 1500s, I can't remember, by a man named Emmanuel, or a boy, honestly, named Emmanuel Galois. Yeah, French. Crazy story about this guy, but he was born into poverty, tried to get into college, but he got really, really angry during the entrance exam and threw it in the guy's face. And he figured out his own form of mathematics, which we call Galois theory today, and we study it in graduate school, by the way. So kid thought of it when he was 19, and now I'm studying it here at 27 when I was in grad school. Makes me feel a little bit inadequate as a mathematician, but either way, he sent out his findings to like 3 big schools at the time. It got lost in the mail twice, and the third guy got it and thought it was just like it was written by a 19-year-old, so he just threw it away. Then the dude got into an argument over a woman and got into a duel, like an actual like straight up duel with guns. And knowing that he was probably going to die, he wrote down his findings and gave them to his best friend. And his best friend found a mathematician, and it ended up being true. Point being, Galois figured out that there is a There is a quadratic formula. We know that one. There's also a cubic formula. There is a formula that solves any cubic. But after that, quartics, so degree 4 polynomials, degree 5, degree 6, degree 7, everything after that, there is no set formula to find all the factors. Very, very fascinating proof. And a very, very important implication is that we only have a cubic formula. Why it stops at 3? That's an interesting question to study. But the point being is, if we have a degree 4 like we have here, there's not really a way to factor it unless we can break it down into smaller and smaller pieces that can be factored. So that is the reason why this is useful. Now, because of that fact that there's no quartic formula, there's no quintic, no hexic or anything like that, we had to discover other ways to factor polynomials along the way. And that's what the next section is going to be about.
Did Galo die?
Yes, he did die in the duel. In the duel. In the duel, he did die. And so, say what?
What a time.
What a time to be alive, killing another person just because you had a problem over who should get to marry a woman, right? And that's crazy.
That's how Hamilton should have handled, like, he should have wrote all the stuff down, gave it to someone before Amber. Like, wanted to get over this.
I love that musical, by the way. That's a great musical. And I do agree as well. You know what's terrible about the whole situation is I'm bummed out, not because he died, but because he couldn't add more mathematics to the world. That's the reason why I'm sad that he's dead. Not because he actually died, but because he couldn't add more math to the world. Guy was 19 and he figured that out. Imagine what he could have done if he lived to 21 and then died of cholera or something like that. It was that time period. So anyways, that is the point. The point is that if we know factors, we can break it down into pieces that we can factor. If it's above degree 4, there's not really a set formula that breaks it down for us. So now the textbook breaks this up into like 5 different theorems. Basically every textbook that I've seen tries to break it down into 5 different theorems, and I wanted to bring it all together. So I'm calling this the big boy theorem, the big boy factor theorem, because I know that's what you kids still say, right? You kids still say boy, right? Okay, good. I'm still relevant. Let f be a polynomial and c be some real number. If one of these statements is true, then all of them are true. They are all, basically, it's a big string of if and only ifs. This is true if and only if this, if and only if this, if and only if this, if and only if this. So what it is the first one is, of course, that f of c is equal to 0. That means, at the same time, that means that x minus c is a factor of f. The one that's a very big, important implication that most textbooks leave out is this next one that says that f of x equals x minus c times something, where this something is the quotient from dividing by x minus c. From dividing by x minus c. So once you know that x minus c is a factor, or if, I didn't even write f of c equals 0. I just wrote f of c. F of c equals 0. That means the same thing as saying x minus c is a factor, which is the same thing as saying f of x can be broken down into x minus c times something else. And then the other two, this one's just the big boy, the original factor theorem, that x equals c is a root / 0. And then the last one is that f of x divided by x minus c has remainder 0. All of those statements mean the exact same thing. It's like different words for the same, different words that all mean the same thing. Like gargantuan, massive, huge, chungus, right? We do we still say chungus in this in this day and age?
No, you should have said your mom.
Your mama, whatever. All those things are all different ways to say the same thing. The same thing is true here. All of these mean the exact same thing. If f of c is equal to 0, you know that x minus c is a factor, and it can be written as x minus c times blah. And that means that f of c is a root, or x equals c is a root, and that therefore there's a remainder of 0. The first three are the far more important implications, most important, most useful parts. So, is x minus 1 a factor of f of x equals 2x cubed minus x squared plus 2x minus 3? And what about x plus 2? What it probably should ask is, if it is, factor it further. So we're going to check out x equals 1. So x minus 1, that implies c is equal to 1. And we're going to use the remainder theorem. We're going to synthetically divide. We could just plug in 1 and see if it works. That would be one option to do. But I'm going to do it this way because I might want to factor it later on. And if I get a remainder of 0, then I automatically know the factorization. So I'll write it here. So 2x cubed minus 1x squared plus 2x minus 3. And all powers of x are present. So we'll do the synthetic division. 1 times 2 is 2. Negative 1 plus 2 is 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. Negative 3 plus 3 is 0. So yes, it is so this tells us that f of 1 equals 0. So it is a factor. And furthermore, so by the remainder theorem, the remainder is f of 1 in this case. That's our c value. And since it equals 0 by the big boy factor theorem, we know that it's a factor. And furthermore, we know the third option is that f of x is equal to x minus 1 times our quotient. And remember, the synthetic division tells you all the coefficients of your quotient. So in particular, it's 2x squared plus x plus 3. Oh, well, I'm not going to box that in. The answer was it is a factor. And now that it's a binomial times a quadratic, and we know how to factor quadratics. Now, unfortunately, I believe this one's prime. I believe this one only has complex zeros. B squared. Yeah, it'll only have complex zeros. But that doesn't matter too much. We can break it down into complex parts if we need. But that's not something we're going to be relevant in this class. So that was x minus 1. What about x plus 2? Maybe it's a factor, maybe it's not. What would c be if we've got x plus 2? Would it be negative 2 or would it be 2? Negative 2, because we have to have it in the form of x minus c. So c is equal to negative 2. Let's check it out. And you could absolutely, if you're just asked to find out whether or not it's a factor, just compute it in your calculator. Compute f of negative 2 and see if you get 0. But if it is a factor, you're going to need to long divide anyways. So 2x cubed minus 1x squared plus 2x minus 3. Synthetically divide. Once again, I'd like you to practice it yourself. You should get negative 27 as your remainder, meaning that f of negative 2 is equal to negative 27 by the remainder theorem. And since that's not 0, that means that it's not a factor. By the way, just as a fun fact about if and only if statements. So what this also means, so each one means all the other four, right? But furthermore, if one of them is not true, then all of them are not true. So if f of c doesn't equal 0, that automatically means that f x minus c is not a factor. That means that f of x cannot be written as x minus c times just a quotient with 0 remainder. It means that it's not a root, and it means that it will not get a remainder of 0. So that's a fun little fact. Yes.
If we look at x minus one, is that a factor? Can't we just know that it is? Because even if the greatest common factor amongst all the terms is one, that would still be true, right?
So that one more time.
Shouldn't we just know that x minus one is a factor like every time? Is there ever a time it wouldn't be? Because if we look at all the factors, even if it is the greatest one, it's still one.
In this specific polynomial,
Well, just any polynomial.
well, x minus 1 isn't necessarily always a factor. It just so happens in this case. But in this bottom one, 1 is not a factor of this. If you plug in 1 into this polynomial, you'll get 3 minus 11. It's negative 8. Minus 1 is negative 9. Plus 19 is positive 10. Plus 6 is equal to 16. So f of 1, m of 1 is not equal to 0. So it all depends. Every polynomial is different. Any other questions?
Yeah, why?
Why?
Because it's not a root, right?
Yeah, it's not a root.
It doesn't hit the x.
Yeah, it will. This polynomial will not hit the x-axis at negative 1.
Okay.
All right. So this is a big use of it. Factor m of x equals 3x to the fourth minus 11x cubed minus x squared plus 19x plus 6, given that m of negative 1 and m of 3 are both equal to 0. Because as it stands right now, there is no way to factor this. We talked about Galois and the fact that there is no quartic formula. So there's no way to figure out what the zeros are unless we're given that information right now. And so, since m of negative 1 equals m of 3 equals 0, x minus negative 1, which is x plus 1, and x minus 3 are factors of m. So we can use synthetic division to factor m. Now, it doesn't matter which one we start with. We can do it with negative 1. We can do it with 3. It doesn't matter. Let's just start with negative 1. That seems like a nicer one to work with. But feel free to start with 3 if you want. So negative 1 divided into 3x to the fourth minus 11x cubed minus 1x squared plus 19x plus 6. Are all powers of x present? All necessary powers of x present?
Yes.
Yes. So go ahead and do this synthetic division. And then I'm going to write something in red down below it. And so don't write the thing I write in red, but I'm going to do this synthetic division at the moment. Once again, don't write the thing I'm writing in red. I'm just letting you guys get finished with the synthetic division, and I'm going to talk about something. All right, so you should get in your bottom row, when you synthetically divide by negative 1, you should get 3, negative 14, 13, 6, 0. You get a remainder of 0, that does mean it's a factor. That means we did this thing properly. If we didn't get 0, that means we didn't factor it right, or we didn't synthetically divide properly, because we're given the fact that m of -1 is equal to 0. Or Phil messed up the problem, one of the two. But either way, but 6,
Yeah, like,
19 plus -13.
what? Sorry.
No worries. And so, by the big boy factor theorem, I'm gonna have to say it that at time every single time. You have to do it too. This means that we can break it down into m of x equals our factor that was given, x plus 1, times 3x cubed minus 14x squared plus 13x plus 6. Now, typically speaking, when this problem shows up for students, they do this step properly, and then they try and do with 3 again, but with m of x again. But that's just going to give you another way to write out m of x as a product of two factors. That doesn't help us break it down any further. I guarantee you, if you FOIL these both out, if you're bored this weekend or if you're trying to fall asleep, FOIL these two things out, you'll get back to m of x being 3x to the 4th minus 11x cubed, blah, 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 blah. So doing it like this doesn't get us to the final factorization. It kind of just makes us go in circles, because as it stands, there's no real way to factor the x cubed portions. We don't have any tools that can break it down. So what do we do?
Can you cancel the second term, the 3x at the top?
So, sorry, say that one more time.
Can you cancel the second part, like, of the
What do you mean by cancel? Just
3x and the 3x on top, and then just subtract it?
these two, these ones right here and here.
Yeah.
So if we were to try and subtract those things, we wouldn't be able, they're being multiplied by two different quantities. One's being multiplied by x plus 1, and the other one's being multiplied by x minus 3. So they're not like they don't have a common factor, so they can't be combined together. So unfortunately, that won't work. But you're onto something by looking at that factor. The fact of the matter is, because m of 3 equals 0, so this is something just to watch. You don't need to write this down. But we know from above that m of 3 is equal to 0. But m of 3, or m of x, can be rewritten like this. We just found that out by doing this synthetic division. M of x could be rewritten like this. So it could also be 0 plus 1 plus blah. And that has to equal 0. Whenever we plug in 3, not 0, 3, I'm sorry. Which is 4, and it has to equal 0. So there's no other way for this to equal 0 unless this piece equals 0, right? By the zero product rule, the only way for a product of two things to equal 0 is if one of them equals 0, at least one. So what I'm trying to say is that this piece, the 3x cubed minus 14x squared plus 13x by 6, it has 3 as a factor as well, or a root, rather. So let's write that down. Since x minus 3 is a factor of m, it must be a factor of this, since it doesn't divide into x plus 1. We know that because the factor, when we divide by x minus 3, it has to give us a remainder of 0. It doesn't go into x plus 1, so it has to be able to be divided into this. So, I'll wait until people have written it down.
So you're saying even if you took out the x plus 1,
Mhm.
you can still divide it
Yes.
by 3, because you would get 0.
Yes.
Okay.
Because that piece, that second piece, has to have x minus 3 as a factor. There's no other way around it. So what we're going to do then is we're going to synthetically divide. Oh, I didn't mean to cut into it. We're going to take 3 and divide it into 3x cubed minus 14x squared plus 13x plus 6.
And that's because you gave it to us.
Yes, because that was given in the problem that you found that m of 3 is equal to 0.
If you only gave us one, would that be our answer?
Yes, we wouldn't be like at this juncture right now with only 2.3 under our belt. This is as far as we could go. You could try, like, you could probably get really bored and start plugging in random numbers and see if something sticks. But that's going to be a very, very impractical method. But we will learn in 2.4 a way around that in just when we get there. So we're going to divide this polynomial that we got for like our quotient from when we divided by x plus 1 by x minus 3. And we're going to use synthetic division because it's going to be faster. There's nothing wrong with doing long division, but if we can skip it, we should. So bring down the 3. 3 times 3 is 9. Negative 5. 3 times negative 5 is negative 15. 13 plus negative 15 is negative 2. 3 times negative 2 is negative 6. And 0. Lo and behold, it does factor that one more. So what this is telling us is that 3x cubed minus 14x squared plus 13x plus 6 can be rewritten as x minus 3 times 3x squared minus 5x minus 2. I'll let you write that down. I've written that quickly. So what that synthetic division has told us is that that quotient factor that we got originally, if you divide it by x minus 3, it will break down nicely into an x minus 3 times the 3x squared minus 5x minus 2. So, point being, we've got this here and this here. We can rewrite m as x plus 1 times x minus 3 times 3x squared minus 5x minus 2. We were able, with this synthetic division, we were able to break m of x down further. So m of x is therefore x plus 1 times x minus 3 times 3x squared minus 5x minus 2. And that we can factor by traditional means. Now, on the exam, by the way, I don't need to see the AC box method or the bottoms up method or anything anymore. I don't need to see it. I've already tested you on that in exam 0. My assumption is now we are okay with that process of factoring, so I don't need to see it. So you can use scratch paper in the future to factor this, but just in the interest of time, this does factor nicely to x plus 1 times x minus 3 times 3x plus 1 times x minus 2. And that is the complete factorization of m. I think it was Hector who said, like, so we were given that fact, but what if we're not given that fact? If we weren't given that fact as it stands right now, we would only be able to break it down into that binomial piece and that cubic. Or we would get really bored and start plugging in numbers to try and figure it out.
No.
Which is not far off from what we're actually going to be able to do in 2.4, but there's a method. So any questions on that? Okay. So the big boy factor theorem told us about the fact that if you know that these points are zeros, then you can write them as factors. And basically what that's saying is the zeros create the polynomial. So this problem right here, I love these problems here. Create an equation of a polynomial f that passes through negative 2 times 100, whose zeros and multiplicities are listed below. We have a 0 at negative 4 with multiplicity 1, negative 1 with 3, 0 with 1, and 2 with 2. So this means, So right here, by big we know that f of x will equal, leave a little bit of space after the equal sign, just enough for a letter, and then write, okay, we know that x -4 is a 0. That means that x plus 4 is a factor. Furthermore, we know that it has multiplicity 1, so the exponent on that factor should be 1. We also know that -1 is a 0 of the polynomial. So x plus 1, right? X minus -1 should be a factor. It's x plus 1. And that has multiplicity 3, so it has an exponent of 3. Then we know that x minus 0 will also be a factor because 0 is a 0 of the polynomial, or 0 is a root of the polynomial. And that has multiplicity 1, so it'll just be raised to the first power. And last but not least, we know that x minus 2 will also be a factor, but it's got multiplicity 2, so it's raised to the second power. Now, I can put an a right here, where a is some constant. So, and I'm going to kind of point an arrow to that. Unless there's any questions on how I've constructed the polynomial thus far. We know those are the zeros, so those must be correspond to the factors, x minus c. Yes, Connor.
The only thing was the 0, does it need to be positive, or can you put plus or minus?
You can put plus or minus, because adding 0, subtracting 0 does nothing. It's just usually to get into the x minus c fashion, you want to write it as x minus 0, but it doesn't matter. Fair question. Fair, like totally valid point. Yeah, you can write plus 0 and it's fine. So the reason why I've written an a here is that any polynomial, regardless of what a is, will have these zeros roots with corresponding multiplicities. I could make a equal to 10 billion, and it will still have those zeros with those multiplicities. That is true. So the problem is, what piece of information haven't I used?
The -2 and the 1.
Yes, the -2, 100. In fact, there is only one polynomial. There is only one polynomial with those zeros that passes through -2, 100. So we're going to add that right beneath it. A big red baboon butt, but only one polynomial, well, only one value of a makes the polynomial cross through -2, 100. Any polynomial. So if they don't give us an initial, like we call that an initial condition. It's an initial condition. It is a piece that is given at the start, i.e. initial, and it's a condition upon f, hence initial condition. So if they don't give us an initial condition, if they just say, find a polynomial that has those zeros to those multiplicities, we can make a whatever we want. We can just make it 1 and just ignore the a. But if they do give us an initial condition like they have here, we have to use that to solve for a. How would I use it?
You put the a -2.
Not the a is -2, the x, right? What's Phil's theorem? If -2, 100 is on the graph, what can you say about f of -2? It equals 100. So we have f of -2 equals a I'll slow down. I'll write.
Thank you.
It's a lot to write. I really like this problem. I'm sorry, I get too excited about it. It's just fun making polynomials that work. And if you're bored, if you ever use the Desmos calculator, feel free to write in it f of x equals a times x plus 4 times x plus 1 cubed times x minus 0 times x minus 2 squared. And that'll give you a slider for a. And what you can see is like also plot the point -2 comma 100. And you'll see if you slide a around, there's only one choice of a that makes it go through the point -2 comma 100. So that's what's happening. There's only one choice. So because f of -2 is equal to 100, given the fact that -2 comma 100 is on the graph, we can plug in -2 in for x. So a times -2 plus 4 times -2 plus 1 cubed times -2 minus 0 times -2 minus 2 squared, that equals 100. I'm sorry, I ran out of space. And then we can compute those. -2 plus 4, that's +2 times -1 cubed, so that's -2 now, times -2, that's +4 times -4 squared, that's 16. So 4 times 16 is 64. Yeah, 64a equals 100. And that means that a is equal to 100 divided by 64, but there's a common factor of 4 that can be, 4. So it becomes 25/16. So that's our a value. As long as a is equal to 25/16, it will cross through the point -2 comma 100. Otherwise, it will never do that. It will eventually hit a y value of 100, but it won't happen when x is equal to -2. So the final answer is that f of x equals 25/16 times x plus 4 times x plus 1 cubed times x minus 0, which you could just write as x, by the way, times x minus 2 squared. And there it is. Yes, ta-da! Very fun problem. We can make up polynomials now.
So we would have to put like the x plus 4 and all that junk with.
So if you want to be cheeky with me, you could just write f of x equals blah times blah and then point to the a and then point to this and call it good. I'll give you full credit. I'll give you full credit. If you don't want to rewrite it totally and just say I'm saving myself carpal tunnel syndrome, then you know what? Fine. I'll give it to you. I'll give it to you. There's a thing that we do in calculus later on where you have to if you want to do it, you have to rewrite the whole problem, and it just takes way too long. And so I have my students just write f of x equals this times this plus this times this, and I'm like, good enough, it's fine. You know what to do. I'm fine with it. It's not that big of a deal. Any questions? Yes.
Where do we get the 64a from? I know there's an a on the previous.
So if you multiply this string of numbers here, that will leave 64. So plug in your calculator, but or do it in your head either way. But this and
all that equals 100, right?
yes, equals 100. And then so when you multiply all the a's, the stuff next to the a together, it will give you 64. Yes, of course. Now the next. Oh, Elita.
On Alex, I want to say it's with zeros and then multiplicity. There's a part where it talks about in the parentheses the x will be squared plus say 4,
Mhm.
and then that would make it that it's 2 and -2 as the answer for the
Zeros.
Does that correspond with this as well?
Kind of, but not really. So if it tells you what the function's factorization is, then you can use. Oh, so I see what you're saying. There is a problem where it's which one of these graphs matches this polynomial. Yes. And so in that case, you could use that information to find this one. It's similar, but this one, we're going to be, instead of being given what the polynomials could be, we're going to create the polynomial ourselves. Because now that we have the big boy factor theorem, we can create this. So notice that it says find a possible equation for G. And we'll explain why it says possible in just a moment. So we have these three zeros. And what we just learned is that the zeros make up the factorization. So we know that f of x, or sorry, g of x in this case, g of x will equal a times x plus 1, then leave a little space and then write x minus 2, leave a little space and then write x minus 4, just a small amount of space. We know that those are the zeros, so that is correct. Those are the factors that are present in G. However, if you were to FOIL that out, that would be a cubic. Does that match what we have? Do we have an even powered polynomial or an odd powered polynomial? Even, because both sides are pointing down. It's the odd ones that have one going down and one going up. The evens have either both going up or both going down. So something's off. What's off? Starts with an M. Multiplicities. We know the shapes of these curves. We know what happens with multiplicities. What is the multiplicity of this one? Is it even or odd? It's even. Even multiplicity. Because it bounces. And even multiplicities bounce, odd multiplicities cross through. Now, here's the reason why it says possible. Without giving more information about this function, there's no way to know whether or not this is, we know it's even, but we don't know if it's 2 or 4 or 10 or 2000. Usually speaking, you can kind of guesstimate that it's probably going to be 2. It's not very jagged there. It's pretty smooth on both sides. Like maybe if it was like this, like maybe we'd be able to say, okay, it's definitely like degree 4 or multiplicity 4 or multiplicity 8. So, but if they don't tell us that, we get the choice. We can say, let's assume 2. So the x plus 1 factor should have an exponent of 2, a multiplicity of 2. Then for the 0 at 2 and the 0 at 4, are those even or odd multiplicities? They're odd because they cross through. Now, the thing is, if this was a question on the exam and you just made these both to the first power, I would give you full credit because I just want you to understand that odd multiplicity crosses through, even multiplicity bounces. However, if you want to get that third date, did anybody try it, by the way? Did anybody try it? Austin, did you try it? No? I need more data, everybody. I need data, okay? But if you want to get a third date, you want to really impress them. You want to wow them with your ability to notice that 2 should have a higher multiplicity than 4 because it has more wiggle. It has more jaggedness. So I'm going to kind of break this down and say this is odd multiplicity. Let's assume 3 because more jagged. But once again, if you wrote to the first power, I'd give you full credit. Because all I need you to know is that it's an odd power. But if we want to be technically correct, the best type of correct, then we would want to write third power.
By jagged, you mean that it's like a little bit horizontally and then vertically?
Yeah, because it's like it's squiggly lined instead of straight line. This one is definitely going to be like as a fun little side note is whenever it makes basically a straight line, it is always multiplicity 1. Because that like when it's multiplicity 1, it should look mostly like a curved line, and it does. It's slightly curved, but it basically looks like a line. So that's the last one. Odd multiplicity. Let's assume 1 because no wiggle or no odd because not jagged. or there's no wiggle, however you want to call it, whatever you want to say, but it has no, it's just almost a completely straight line. So it's going to be to the first power.
So.
Hmm?
Doesn't matter, but because it's causing the y-axis at -4, and then it's pointing down too,
Yes.
so wouldn't it be a negative?
Excellent point. So if they did not give us a coordinate point that we could utilize to solve for A, we would have to make A equal to -1. We can't make it whatever we want. We have to make it a negative number. So you can make it -2, you can make it -10,000 if you're not given an initial condition. But it has to be negative because this polynomial has to drop downwards. If it was going the other way, like that, then it would have to, then you'd make A equal to 1. However, this is giving us, we're given an initial condition. It's giving f of 0, right? If I were to give this on an exam, I would make sure to plot, like show this point. There is a y-intercept at 0, 4. So f of 0 equals 4, which will allow us to solve for A. All right. So we have a point. We have an x value and a y value. So on an exam, if I were to do it, I'd probably give you either that point, or I might give you 3, 2, or maybe I'd give you like 5, -4. I would give a point that you could use. And I'd probably put in the problem statement, note that the graph passes through blah, so that you can utilize that point to solve for A. So let's do that. F of 0, well, that would be A times 0 plus 1 squared times 0 minus 2 cubed times 0 minus 4 to the first power. And that has to equal 4. 1 squared is 1. -2 cubed is -8. Times -4 is 32. So you got 32A equals 4, which gives us that A is equal to 1. Wait, -4. -4. F of 0 equals -4, everybody. I'm sorry about that. So please make it equal to -4. Sorry about that. So that should make it 32A equals -4. And A is equal to -1/8. As Hector mentioned, it should be a negative number for our constant out in front, coefficient. So we've got it. Therefore, g of x is equal to -1/8 times x plus 1 squared times x minus 2 to the third times x minus 1 or x minus 4 to the first power. And so if this was a question on the exam, by the way, you can make it whatever you want. If you really wanted to troll me, you could use x plus 1 to the 200th. You could totally do that. And it would be fine. Your A value might become much smaller because the higher the degree, the higher the multiplicities, the larger these numbers get quite fast. And so in order to make it go through 0, -4, it'd have to be a very, very small number to vertically shrink it, to vertically compress it. But either way, you could totally do that. Yes.
So in the same fashion that we used -4 and 0, could we also use -1 and 0?
Ah,
Since that's the first point.
excellent question. And I'd love, so let's explore that. We're given -1, 0. So that the problem though, if we try and do that, g of -1 equals A times -1 plus 0, or -1 plus 1 squared times -1 minus 2 cubed times -1 minus 4 equals 0. Do you see the problem? That equals 0. So we're just going to get 0 equals 0 because this is going to get completely wiped away. So the zeros will make the whole thing 0, and we can't really use them to figure anything out. So great idea, but it unfortunately won't work for us because it doesn't give us enough. The point that we get, like a non-zero point, is what we need.
Gotcha.
All right. This problem's very, very fun, and I'll give you a hint on to do it, and then we'll take our first break. So if x minus 2 is a factor, what can you tell me about f of 2? If it's a factor, that means that 2 is a root for a 0, so it equals 0. So plug in 2 for x, because k is some fixed number. And you should be able to find out 2 values of k that work. It's a pretty fun problem. That'll be my hint. And then once again, I meant to send it out yesterday. I didn't. I got behind, and that's why I don't have your exams graded yet. I was trying to finish them. I just didn't get a chance to get all the way through it. But I will also send out the synthetic division video to show you why it works. If you want to know, you don't have to watch it. It's just for funsies. It's just if you want to know what we're doing and why it works. So yes.
When it comes to like in Alex, you go back up. Yeah, you know what, when you're planning those points, it's kind of still confusing, like how it wants it.
For sure.
And especially because Alex can be really unforgiving sometimes, because
Yeah.
like if you do really good, it won't reward you, but let's say it gives you like, there's like a meter.
Mhm.
Just like if you do it good 2 times, there'll only be 3 chances. But
Yeah.
if you mess up a certain amount, you're like, okay, no, you'll have to do it like 3 more times. It's really annoying. And plus, I was doing those modules, and I got 3 of them done. They said, "Oh, congratulations, you already learned them," and didn't count the other ones I already did.
And believe me, I understand the frustration
That's
there.
very
Like
mean.
it is. I'll tell you though, learning's not nice. It's not a fun procedure. Learning takes a lot of time and it takes a lot of effort. That's why I don't like the other homework systems. I know it is frustrating, but I'd like you to think of it instead of trying to think of it as like losing progress and and doing that. Think of it as extra practice for the final exam. The final exam is cumulative. Final exam covers all the material of the course. The more practice you get, the more prepared you're going to be for the final exam. And Alex does something that no other program is able to do in at least right now, and it's the knowledge checks that it does. As frustrating as they are, it is the only way for us to get a little chance to go over material when I can't do it in class. If we had recitation sections like some colleges do, which I can't expect of community college, it's not possible. We don't it's just not. We don't have graduate students to force to do things for our for pennies on the dollar, unfortunately. Or if this was like high school where I get to stay with you 5 days a week, we could go over remediation for older stuff, but I don't get to have that opportunity. So that's why I really like the Alex system.
A way to be able to make it so that we are able to persistent knowledge checks later on.
There is a way to do it where you ask me and I can delay a knowledge check, but that's kind of a hard one because I have to make sure I see it in my email when like right away so that I can activate it right on the top of your head. It doesn't hurt. So like, hey Phil, I'm vibing right now. Can you hold off on the this knowledge check for a little bit and then I can delay it for a little while?
Does that affect their grade?
No, knowledge checks don't.
They're annoying because they're like, they get in your way. Like, no, sure.
I understand. It's totally understandable. I get that. And so if that happens, you're free to email me about it. And like if I'm able to, I will delay it for a little while. I'm going to ask Alex about that if we can make sure like that'd be a good feature to allow teachers to do, like to maybe over the weekend, make sure that no knowledge checks happen on the weekends when people are usually finishing off their assignments. That'd be a good thing. I'll email Alex about that. So, any other questions?
If you do good,
Are you doing 127 in spring?
No, not the one, not myself, not next semester, but my wife is, and she's better at teaching 127 than I am. And I'm not just saying that she likes that material more than I do. I like trig, but it's not my favorite. I like teaching calculus more in this class. I like teaching 126. I like functions. Yes.
So when are we receiving back our test?
On Tuesday. On Tuesday, I'll have him back, definitely. Okay, let's take our first break. Let's come back at 10:56. All right. So, getting to what Ben was discussing, which was the idea of how do we factor it, essentially. We have a important thing in what we call this section is called the zeros of a polynomial. And we have one of the most important theorems of all of pre-calculus, despite it being called the fundamental theorem of algebra. Well, I guess it's like, I mean, a lot of pre-calculus is just algebra stuff. So if f is a polynomial of degree n, then f has at least one zero slash root, which that's what the original statement of the fundamental theorem is, fundamental theorem of algebra is, which is not very exciting as it stands. But as a consequence, all polynomials can be factored into linear terms. What I mean by that is f of x can always be, a polynomial can always be written as a times x minus c sub 1 times x minus c sub 2 times dot times x minus c sub n. That's the far more useful aspect of it. What it tells us is that, so the better version of the fundamental theorem of algebra says that everything can be broken up into linear factors with complex coefficients. So those, like, as I've shown you right here, p of x equals 2x to the fifth minus 5x to the fourth minus 12x cubed plus 40x squared plus 10x minus 75. That thing does get factored down into 2x plus 3 times x minus the quantity 2 plus I times x minus the quantity 2 minus I times x minus the square root of 5 times x plus the square root of 5. Which, if you want to get it into the perfect format, you'll factor out an a, you'll factor out the 2 from the 2x plus 3 and rewrite it like that. And so the other way to write it is that every polynomial can be broken down into linear terms and irreducible or prime quadratics. So in the previous section, I gave you this function, m of x equals 3x to the fourth minus 11x cubed minus x squared plus 19x plus 6. And we were given the fact that m of -1 and m of 3 were equal to 0. But how would we have factored that if we weren't given that information? The fundamental theorem of algebra says that it can be factored somehow, but how? And as we said, Galois has showed us that there is no quartic formula, there is no quintic formula, so there must be some way to do it. And there have been many different ways to figure these things out. Many mathematicians have plagued themselves with trying to figure out ways to break down a polynomial nicely. One of them was called Eisenstein's criterion, not Einstein, but Eisenstein, which is really, really strange that another scientist with the name Eisenstein, very, very similar. He, of course, it's a he, because of, good old sexism, but either way, he figured out one way, but but it's very, very impractical unless you're studying upper division mathematics. But one of them that is practical is called the rational zeros theorem. And what it says is let f be a polynomial with integer coefficients. If the polynomial doesn't have integer coefficients, this kind of goes out the window. So that is f of x is equal to a sub n x to the n all the way down to a sub 0, where a sub n through a sub 0, they're all integers. Then the possible rational zeros of the function are of the form x equals p sub 0 divided by q sub 0, sorry, plus or minus, where that is plus or minus the factors of a sub 0 over the factors of a sub n. P sub 0 divided by Q sub 0, where P sub 0 is a factor of A sub 0, and Q sub n is a factor of A sub n. So I remember learning this in school, and there was no fun way to memorize it. I couldn't think of any mnemonic device, and it came across me. So you might be wondering, why is there a toucan with a top hat and a pencil, or not a top hat, a graduation cap? And so my idea was to remember not Toucan Sam, but his much smarter relative, Pooh-Can Sam. Is it stupid? Yes. Maybe it makes you memorize it though. Because like a P, like, so yeah, it should be Pokin Sam, but that doesn't have as much of a ring to it. So maybe Pooh-Can Sam with a Q instead. So P sub 0 is that kind of tells you immediately we're talking about A sub 0. Q sub n, we're talking about A sub n. That's the way I tried to memorize it. P sub 0, factors of A sub 0. Q sub n, factors of A sub n. So what do I mean by this? How do we use this formula? How is it useful at all? It's telling us that if we have a rational 0, meaning a fraction or an integer, all integers are fractions at the end of the day, because you can just divide by 1. But if it does have nice zeros, then they are going to be of the form plus or minus factors of A sub 0 over factors of A sub n. So let's see it in an example here. I'm giving you this quartic polynomial, and we're going to list out the possible rational zeros. So the factors of A sub 0, which equals 8. What are the factors of 8? 1, 2, 4, and 8. Those are all the possible factors of 8. 1, 2, 4, and 8. And the factors of A sub n, which in this case is -4, ignore the sign for a moment and just look at the 4. That would be 1, 2, and 4. So, by Pooh-Can Sam, the possible zeros are x equals plus or minus. And what we're going to do is we're just going to start with one of them. I'm going to work with just the first. I'm going to look at all the different factors of A sub 0 over the first factor of A sub n. Then I'm going to do it again with the second factor of A sub n. And then I'm going to do it again with the third factor of A sub n. So what it's going to be is plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 8 over 1. 1 is a possible factor of A sub n, right, as we see right here. And so I'll do any factor of A sub 0, 1, 2, 4, or 8, divided by 1, which is, I'm doing it so we see it in the format of the theorem, but yes, that's going to be 1, 2, 4, and 8, right? Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, because dividing by 1 doesn't do anything. But now we'll do the next set. We've gone through all the possible combinations where A sub n's possible factor is 1. Now we'll move on to 2. So we should get plus or minus 1/2, plus or minus 2 over 2, plus or minus 4 over 2, and plus or minus 8 over 2. I'm going to move this over a little bit. I ran out of space. That was the other, that was one of the other factors of A sub n as a denominator. And then we'll go on to the last one, 1/4. So we get plus or minus 1/4, plus or minus 2/4, plus or minus 4/4, and plus or minus 8/4. It's a lot of them. However, there's some good news here. We can shorten it, we can reduce it because there's some repeats. I'm going to highlight the repeats. 2 over 2, that's just equal to 1. And we already have one. 4 over 2. That's equal to 2. And we already have that. 8 over 2. That's equal to 4. We already have that. 1/4 we don't have. 2/4. That's one. No, not that one. 2/4. That's equal to 1/2. And we already have that. 4/4. That's 1. And we already have that. And then 8/4. That's equal to 2. And we have that. So these are all repeats. So the actual list is going to be x equals plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 1/2, and plus or minus 1/4.
But if I type this on Alex, it should get this. It should accept it, right?
Yes. So I believe you have to put the plus or minus each time,
Yes,
unfortunately.
it does, yeah.
Yeah, but the good news is there's a button for it. You don't have to. So just keep pressing that button each time. You don't like. I think it'll accept it even if you write all of them. It might just give you kind of a comment saying you can simplify it. But the idea is that those are the possible. These aren't the actual zeros. That polynomial can have at most 4 zeros because it's a degree 4 polynomial. At best, that thing can be factored into 4 linear parts because it's a degree 4 polynomial. A degree 5 polynomial has 5 factors. A degree 6 polynomial has 6 factors, and so on and so forth. Maybe they're repeats, maybe they're not, doesn't matter. But that's a total of 1, 2, 3, 4, 5, 6. That's a total of 12 different potential zeros. What the rational zero theorem tells us is that if it has rational zeros, if it has rational factors, it's going to be one of these numbers. So that might seem like, well, that doesn't help very much, but it actually does. Instead of having to test every number in existence, every integer and rational number in existence, we only have to test 12. And going from infinity down to 12, that's a pretty narrowing option. We went from infinity to 12. So let's see it in action. Fact of the polynomial, 3x cubed minus 7x squared minus 22x plus 8 completely. So as it stands right now, it is a quadnomial, so we could try and factor by grouping, but that won't work. We could try and split it down the middle, but that's not going to work, unfortunately. And we don't know the cubic formula. Hell, I don't even know the cubic formula off the top of my head. So we're going to use the rational zeros theorem, which, by the way, I should have mentioned, let's call this RZT. Because I don't want to write rational zeros theorem every single time. That takes way too long. Riz. It's got the Riz, as the kids say, right? Do we say Riz still? It's a nice theorem. Got the Riz. Okay, so how did I want to write this one? Yeah. The possible zeros. So the factors of a sub n. 1 and 3. Nice. Only 1 and 3. We don't have 3 factors. We don't have 5 factors. The larger the number, the more factors you have to check. But the a sub n is 3. That's our leading coefficient. And the factors of 3 are 1 and 3. The constant term, 8. So a sub 0 factors are 1, 2, 4, and 8. And so it's Pooh-Can Sam, a sub 0 over a sub n stuff. A sub 0 factors over a sub n stuff. That's why I said Pooh-Can Sam and not Can-Poo Sam. Yes.
So is the leading coefficient always a sub n and the constant is a sub 0?
Yes, that's correct. Because n should be the largest number in the set and a sub 0 should be the smallest one. So looking at it, and the way we're going to do it is so it's Pooh can Sam. So it's the A sub 0 factors over the A sub n factors. The convention is to fix the A sub n factor and then do all the different ones for A sub 0 and then move on to the next one in systematic order. But there's nothing stopping you from doing it in the reverse order. So the possible zeros are plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 8 over 1, and then plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, and plus or minus 8/3. Now, in the future, I'm just going to rewrite these. I'm going to reduce the fractions as I go along. So I'm not going to write it anymore as 1 over 1. I'm just going to write 1. 2 of 1, I'm just going to write 2. If I see 2/4, I'm going to write it as 1/2. Ben, do you have a question?
Yeah, originally it was Q over O divided by QO, right?
QN.
QN, excuse me. So why is it that we're putting the constant on the bottom now?
We're putting the factors of A sub n on the bottom. Because it's P sub 0 over Q sub n. Who can Sam? So
Okay.
That's snappy Starbucks person, really good. You're like, it's QN.
QN. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, and plus or minus 8/3. Okay, that is a total of 1, 2, 3, 4, 5, 6, 7, 8. That's 16 numbers to check. Do you want to do that?
No.
No. So the good news is, so pro tip, try the easier numbers first. And use your calculator.
And you can eliminate too, right?
This time you can't eliminate any of them. They're all of them are unique. So I actually changed this last semester. When I originally taught this, I did it the way that I've always done it, which is I'll just keep synthetically dividing until I get the answer. But that takes a long time. It takes a lot of space on a problem, and it takes forever when there's a faster way. So remember the brute force versus the remainder theorem. If you're just trying to see whether or not something's a factor, and like they give you the thing to check, the remainder theorem is great for it. But otherwise, since we have a calculator, let's use it. And so people watching the recording, sadly, you won't be able to see this, but I'm going to show you how to use your calculator to do this. So it's easier to try the nicer numbers first, and then use your calculator to help you out here. If f of c equals 0, i.e. when you plug in one of these numbers, you get 0, you know that it's a factor, and then you can do the synthetic division. So I'm going to pause the recording so that people, well, I mean, I guess I could keep it running. It's not a big deal. I'm going to switch over to the document camera so you can see what I'm going to do. So on your page, let's make that less blurry and zoom in. All right, so let me move this out of the way so I can get. So our polynomial was 3x cubed minus 7x squared minus 22x plus 8. Let's just start with 1. Let's start with 1. So that would be, if I were to plug that into my calculator, and I want you to be very, very particular. I want you to use parentheses because we're going to be plugging in negative numbers as well. And so you're going to need the parentheses anyways. You'll see why. So let's plug in 1 raised to the 3rd power. I know that 1 cubed is 1, so I don't really necessarily need to, but that's only because it's 1. I'm going to be testing a bunch of numbers. So I want to just make it in the proper format. Minus 7 times in parentheses, it's 1 squared. And then it's minus 22 times 1, and then plus 8. So on your paper, I want you to write f of 1 equals, what is it? Negative 18. So not a factor. All right, then let's try negative 1. So my calculator, as long as you've gotten the ones that I've suggested, they have a storing feature. So what I can do is I can press back, and now I'm inside that computation again. I can just change all the ones to negative ones. Negative 1, negative 1, negative 1. And that's it. There was 3 instances of negative 1, and I've done that. Equals 20. So I want you to write on your page f of negative 1 equal 20. So that's not a factor either. Let's keep going systematically. Instead of doing synthetic division each time and keep getting it not working out, like if you look at any of these ones where you're trying to do it that way, it just takes way too much space. So then we'll move on to 2. So we'll just delete the negative 1 and replace it with a 2. Delete the negative 1, replace it with a 2. Delete the negative 1, replace it with a 2. And I get negative 40. Not going to work. With 2, it did not work. We got negative 40, and so no luck. But let's try negative 2. So we'll just go back into the function, change the 2 to a negative 2, change the 2 to a negative 2, change the 2 to a negative 2, and then press enter. Ha-ha! F of negative 2 equals 0. So I'm going to switch back to the actual screen again. So f of 1 was equal to negative 18. It was not a factor. F of negative 1 was equal to 20. It's not a factor. F of 2 was equal to negative 40. Not a factor. But f of negative 2 was equal to 0. So that means that x minus negative 2, which is x plus 2, is a factor. So, by the big boy factor theorem, I can now start breaking it down with synthetic division using a C value of negative 2. Negative 2 divided into, let's see here, 3x cubed minus 7x squared minus 22x plus 8. All powers of x are present. So go ahead and start synthetically dividing. Right. Negative 3, negative 6, negative 13, 26, plus 4, negative 8, 0. And we should get 0 as a remainder because it is, in fact, a root. We just found that out by plugging it in and getting 0. So this is the trick to get around it. So you can use your calculator to your advantage. Please do so. Instead, the way I originally did it, so while people are finishing that up, I went, okay, 1 divided into 3, negative 7, negative 22, 8, 3, 3, negative 4, negative 4, negative 26, negative 26, negative 18. Nope. Then I tried negative 1 and do the same thing. 3, negative 7, negative 22, 8, 3, negative 3, negative 10, 10, negative 12, positive 12, 20. Nope. And I would go like that. And that takes way too long. It's a lot of space just to find 1 0. Remember, we had to test 3 numbers in order to get it, or test 4 numbers to find the first 0.
What makes it a factor?
It makes it a factor if the remainder is 0. Or another way to say it is that if you plug it into the function, you get 0.
So if no 0.
Yep. If no 0, then no factor. Ben.
We just did the synthetic division just to double check, right?
We did it for 2 reasons. 1, to double check, but 2, to find the next factorization. So this tells us, therefore, that f of x is equal to x plus 2, the piece that we divided by, times our quotient. 3x squared minus 13x plus 4. And that is a quadratic. We could use RZT again, but easier to factor like normal. Because we can, like, as soon as it breaks down into a quadratic, we have ways of factoring quadratics, right? We know our AC method or our bottoms up method or our AC box or snowflake, whatever you want to use. And this thing, just to save on time, this factors to x plus 2 times 3x minus 1 times x minus 4. Now, as a fun fact, look at the possible zeros. The zeros of f were -2, which is one of the possible zeros. 1/3, that shows up right there. And 4, which is one of the possible zeros. So all of them actually ended up being in that collection. So you have that at your disposal, which is pretty nice. So let's see it in action again, and then we'll take our next break. Unless there's any questions on that. So Pooh can Sam, factors of a sub 0, because Pooh, p sub 0, over factors of a sub n, the qn can. I also liked it, by the way, because there was a statement that one of my favorite teachers said that mathematics is very you need to be your own toucan Sam. You need to follow your nose, right? To the flavors of math wherever they grow. Oh yeah.
Continue going until you find another one that works, or
So we're gonna do that in the next not the next one, but the one after that. Oh no, the next one will use it. So sometimes we need to break it down even further. Yes.
On the test, do you want us to just find one, like we did on -2? You want us to find all the
The rational
all the
zeros.
rational zeros that all the digits from possible zeros are.
So if you get it down to a quadratic, don't bother using RZT again, because we know how to factor quadratics. And I promise you, if there is a question on the exam that requires you to use this fact, it will be nice and factorable. It will not be something obscenely difficult to factor the quadratic portion of it. But that being said, yeah, if it has more than just as we'll see in the next example. Let's see the next example. So P of x is equal to x to the 4th plus 4x cubed plus 3x squared minus 4x minus 4. So luckily for this one, the factors of a sub n are just 1. And a sub 0, the factors of a sub 0 are 1, 2, and 4. So the possible roots of the possible zeros are Pooh can Sam. So a sub 0 factors over a sub n factors would be plus or minus 1 over 1, which is 1, plus or minus 2 over 1, which is 2, and plus or minus 4 over 1, which is 4. So we only have to check 6. That's not 6, that's 4, so 6. We only have to check 6. That's nice. So we'll just plug them into the function. P of 1 is equal to, we'll use our calculator again. So 1 to the 4th, yes, I know that's already 1, but we're going to be using this to check things. So 1 to the 4th plus 4 times 1 cubed plus 3 times 1 squared minus 4 times 1 minus 4. It equals 0. Awesome. First try. So x minus 1 is a factor. If f of c or p of c equals 0, then x minus c is a factor. So since p of 1 equals 0, x minus 1 is a factor. So we'll use that to our advantage. 1 divided into 1x to the 4th plus 4x cubed plus 3x squared minus 4x minus 4. All powers of x are present. Go ahead and do the synthetic division. Wait, no, positive 4, positive 4. You got 0. You should get 0 as your remainder. If you didn't, that means you made an error somewhere. And so that's like, and this goes to Ben's question about whether or not you could check your, like, whether or not it was supposed to check your work. So, as you probably will find out as you try and use your calculator to test these things, every once in a while you make a mistake. Maybe you change all of them to -1 except for one of them, and that will fundamentally change it, right? Because instead of plugging in -1 every time, you're plugging in -1 for all of them except for one on the other, and that will give you the wrong answer. So this gives you a way to check it. So if you get a fluke answer of 0, then check it and you will see that it doesn't work out. So this means that p of x can be broken down as x minus 1 times, we reduced the power by 1 because we divided our degree 4 by a degree 1, leading us to a degree 3, so x cubed plus 4x squared, or to 5x squared, excuse me. 5x squared plus 8x plus 4. And that is a quadnomial, x cubed plus 5x squared plus 8x plus 4. That is a quadnomial. So we could try and break it up with factoring by grouping, but it's not going to work. Sadly, it's not going to work. So instead, we have to use the RZT again, because x cubed, cubic polynomials, we don't have a way to factor them. There's no method, there's no guaranteed method that works for all of them, like the AC box method and stuff. So we need to use RZT again.
Could we use 1 again?
Yes, we could. It might be a repeat. So let's call this function q of x for now. So factors of a sub n are just 1, and the factors of a sub 0 are 1, 2, and 4. Just like last time, luckily. That's just a fluke that happens. Sometimes it ends up being the same. Most of the time it doesn't. Hector, yes.
You know how we did it on the earlier one? Could we just keep on using the same numbers? Because if it makes it 2 for 1.
Yes, see, that is a good point. So Hector was mentioning something very important. Because those were all the potential zeros, then you don't even, that's a good point. I never really considered that actually. So you can actually just test the same zeros on that one. The only reason why you might want to change it, that I think about it, is that it just so happened that this one had the exact same things, but every once in a while it changes and it reduces the amount of ones that you need to check. But at the end of the day, does it matter? Not really. You can keep going through. But just to get practice with the RZT. So, but no, Hector's absolutely right. You could just keep checking 1, -1, 2, -2, and 4, and -4, and see if those work. This one worked out very nicely because there's only 6 choices. But as you'll see in other examples, you can get like 20. And so once you reduce it down, it goes from 20 to maybe like 10. And so you don't have to check all 20 this time.
Also, the more we do this procedure normally, the less factors.
Yes, it starts reducing the amount. That is the nice thing.
I like that.
So the possibles here are plus or minus 1, plus or minus 2, plus or minus 4. And so Q of 1, let's check that out. So that would be 1 cubed plus 5 times 1 squared plus 8 times 1 plus 4. That's equal to 18. So nope. How about negative 1? In fact, I want you to notice something. I'm not going to bother testing any more positive ones. Why? Just a little nifty trick to notice. Notice that every term in Q, this new one that I'm calling Q, this pink function I'm calling Q, every single term is positive. So if I plug in a positive number, it's just going to be adding a positive plus another positive plus another positive plus another positive. It'll never be 0. So I don't need to test any positive numbers anymore. That can happen every once in a while. If you look through the textbook in this section, there's a thing called Rene Descartes' rule of sign, which is a way to kind of reduce the work that you need to do, but it's so niche, it's so unnecessary. So don't worry about Rene Descartes' rule of sign or anything like that. If it talks about it in ALEKS, don't bother. It's not useful. It used to be useful back in the day. It's no longer useful now that we have calculators. So Q of negative 1, I'm just going to change all these ones in my calculator to negative ones. And I get 0. Sweet. All right. So I'm going to synthetically divide Q of x by x minus negative 1. So x plus 1 is a factor. So I'll do negative 1 divided into that polynomial, 1x cubed plus 5x squared plus 8x plus 4, bar right before our constant term. All powers of x are present and accounted for. Perform the synthetic division. 1 times negative 1 is negative 1, and 4. That gives me 4, and then negative 4, and that gives me 0, as I'd expect.
You say it like a, sorry, all
Yeah.
present and accounted for a week.
Well,
Tell me all present and accounted for.
or yes, sir. All right, so you should get 144. So using that information, we now have that P of x can be broken down into an x minus 1 times an x plus 1 times an x squared plus 4x plus 4. Are there any questions so far? Why? Why? Because it's fun. We're finding out the zeros. Fun fact, I think I mentioned this at one point when we were talking about how to factor quadratics. There used to be, like, it used to be a thing that people would do, mathematicians would do. They'd try and create their own polynomials and see if another person could solve them. It was like Beyblades, right? If we ever played Beyblades, I never did, but I'm assuming that's what Beyblades is. You stand up with each other, you bring out your cool Beyblades, your polynomials, if it were, and you test them against each other, and then whoever could solve them faster got more respect. And so if you knew about the rational zeros theorem and no one else did, so they were very secret about these things at the first time because it was trying to be like cooler than the other kids on the block. You know, math cool. Yeah, some PvP, you know, some good old PvP. And then they'd if you lost, you were the loser. You were considered a dummy. And so, anyways, this was probably a really nifty trick to know about if you were trying to solve polynomials, solving how to factor them. So that's why this is cool. That's why this is useful. You don't want to be accidentally dropped into one of those situations and not be able to solve them, not be able to factor it, would you, Thomas? You want to be the cool kid who knows how to factor all of them, and now you can be. So this thing, now that we've got a quadratic, we can factor that like normal. We could use the RZT. We totally could, but it's not going to be necessary. We can use our regular process of factoring to see that this becomes x plus 2 times x plus 2, or x minus 1 times x plus 1 times x plus 2 squared. Either way is acceptable.
For the John Doe, it would be X.
No, John Doe would get full credit. I mean, yeah, he would say the first one. And then Alex would correct him and say, you can combine those and write that as x plus 2 squared, right?
No, the John Doe answer would have been like X minus 1 squared and X plus 2 squared. That would be the John Doe answer.
Yeah.
But because the X and the minus the plus won't do it. So only the 2 is one.
Exactly right. Okay. Let's take our next break unless there's any other questions. And how much more do we have? We have this one and this one. That's it. Okay, cool. We're getting there. We're getting there. So people watching the recording, go do some. Oh, you want that back up there? People watching the recording, go do some squats and some push-ups. All right. So we've got this one next. We've got 2x to the 4th minus x cubed minus 20x squared plus 5x plus 50. Okay. So this is to show you, as Hector has suggested, we could just keep testing the ones from it. This one actually reduces the amount that you need to check afterwards. So factors of a sub 0 or a sub n are 1 and 2. The factors a sub 0 are 1, 2, 5, 10, 25, and 50. Any other ones? 4 doesn't go into it. 6, no. 7, no. That's it. Yeah.
We're still assuming plus or minus as well.
Yes. We're going to add the plus or minuses at the, afterward, or right now. So the possibles are plus or minus 1 over 1. So that's 1. Plus or minus 2 over 1, plus or minus 5 over 1, plus or minus 10 over 1, plus or minus 25 over 1, plus or minus 50 over 1, comma. And one thing as a pro tip, another pro tip, as I have done this for a long time, it's never the big numbers. It's never 50. It's never 25. It's even rarely 10. It's usually a number between 1 and 9. Maybe it's a fraction, but also like the really small fractions, like 1/50th or whatever, not going to be it. If you ever have that happen on a problem, please let me know. I would love to study that. That's amazing that happens. But then you also have plus or minus 1/2, plus or minus 2/2. Oh, wait. Let me write that better. Plus or minus 1/2. Because now I'm switching over to the other factor of a sub n, because it's Pooh Can Sam, a sub 0 over a sub n. Yes?
If we start this sequence with plus and minus and don't include it on the rest, will you count that as full credit?
I will totally count that as full credit on the exam. I'm doing it so that because Alex is going to want you to do that, but on the exam, if you write plus or minus and then write other things, that's fine with me. Just make sure you remember to check the pluses and the minuses of all of them. And then so plus or minus, it would be 2 over 2. But that's 1, so I don't need to write that 1. Then I get 5/2. Then 10/2 would be 5, but we've already listed 5, so I'll skip that one. And then plus or minus 25 over 2. And then 50 over 2, plus or minus 50 over 2, that would be 25. And we already have 25, so I don't need to write it. So I've got those ones. I'd like you to start working through it now. Like try and find it. Use your calculator if you have one. If someone needs a calculator, I have one. I have an extra. But I'm going to slowly start filling in the problems. I'm going to work systematically from 1. I try and go through the numbers less than 9 first, and then the fractions, and then the other ones. But I've never it's always been the case that I've always been able to find at least one between 1 and 9. Like the chances of it not happening that you get one that's in between -9 and 9 is so slim. So I'm going to start doing that. So this is the first part so far. And I just tested 1, -1, 2, and -2, and that's when I found -2. So I started working with that. But you might have found a different number to work with at first, and in which case, then go ahead and work with that one. But you'll get the same answer at the end anyways. Mention this. And so, I wanted to stop here one more time. So notice now that the number of possible zeros has been reduced. We no longer have to worry about plus or minus 50. We no longer have to worry about plus or minus 10. And we no longer have to worry about plus or minus 2. So yeah, we saved a lot of time. Yeah. Sorry, one other thing that I wanted to mention. So notice that we already checked 1, -1, and 2, right? And we did not get a 0 from those. So I'm going to mention right here, since, well, let's use a different color. Since y of 1 didn't equal 0, x equals 1 won't be a 0 of q either. Same for x equals -1 and +2. So I don't even need to bother checking 1 and -1. It doesn't hurt to do so. It's not going to cause any problems at the end of the day. But if you check a bunch of them first and none of them are zeros, you can immediately eliminate them from the pool of testing values. Because once again, if it wouldn't magically become a 0 of this one, because if it did, then it would also be a 0 of y. Does that make sense? Can we say that again? So once again, we already tested 1 in the original polynomial, and it did not equal 0. Since this is just another way to write it in a factored format, when you plug in 1, it's not going to give this to be 0, because otherwise it would be a 0 of y. So that's something nifty to check. So we don't need to check 1. We don't need to check -1. 2 was already excluded from the possible zeros of q of x anyways. So I've tested a bunch of them. I mentioned it during the pausing of the recording that once I tried 5 and -5, I didn't bother checking 25 because I doubt it's going to be the thing. I can count on 0 hands the number of times any number larger than 10 has ever worked as a 0 of the polynomial. So I leave those as a last resort, and that's why I started working with the fractions. I tried 1/2 and -1/2, and it didn't work. So I tried 5/2, and it did work. So that's my C value. And now what I've got to do is I've got to start working through that here. So, but it's just a fraction. It's the same concept. Hopefully we don't have to deal with any more fractions than we have to, but let's see. Bring down the 2. 5/2 times 2. Luckily that cancels that out and we get a 5. That gives us a 0. 0 times 5/2 is 0. So we get -10. -5/2 times 10, that's really going to be 5 times -5, so that's -25. And that equals 0. So we are nearly done. So y is equal to x plus 2 times x minus 5/2 times 2x squared minus 10. And that function right there, 2x squared minus 10, has a common factor of 2 that can be pulled out front. That's 2 times x squared minus 5. And do you remember when I was talking about the fact that anything can technically be a difference of squares? Now, on ALEKS, they'll accept it like this. They'll accept it like this because you can't technically break down x squared minus 5 into linear terms with nice coefficients. But we can break it down further by making that x plus square root 5 times x minus square root 5. So at the end of the day, y equals 2 times x plus 2 times x minus 5/2 times x plus the square root of 5 times x minus the square root of 5. All right, in all its glory. Any questions on that? So, yes, it is a lot of testing, but luckily, I mean, imagine if we didn't have calculators.
Oh my god.
It would be a really long process. Because either you could try and do those calculations in your head by brute force, which I wouldn't recommend that. That's going to be very, very annoying. Trying to do 2 times 5 cubed minus 5 times 5 cubed. Well, that would be nice. Well, no, that won't be nice. And then, or you could do the synthetic division check, but even then you'd have to check 4 of them. You'd have 4 different synthetic divisions that didn't turn out. It'd be a real waste of time. So please use your calculators on these ones. Use it to your advantage. I try to minimize the amount of stuff that's here. There's basically like only 3 topics from this section, where one of them is just writing the potential zeros, and then the other ones are usually using the rational zeros theorem to factor it, but it's usually no more than a degree 3, at most a degree 4. So, okay, any questions? All right.
Oh, I have one. Do we have to simplify it all the way to the one that's all like to your last result, or if we put the first one y equals
The one
equals
that
to
the 2x squared minus 10 version.
yeah.
Yeah, that would be acceptable. I would give you full credit on the exam if that was the case.
It's all the way simplified, right?
Yeah, like I would love it if you were to factor it further by realizing that technically speaking, you can think of x squared minus 5 as a difference of squares and break it down.
Yeah.
But I'm not going to be a hard ass on that one.
Thank you.
Okay. In the interest of time, I'm going to skip this one. This one might be a fun one to do at home. So the key thing, use RZT to factor. Because right now it's a quartic. And notice that there's no x cubed term. No x cubed term. And so you'll use the RZT to find the factors, factor it. You have the expanded form, which means you can find the end behavior. Then you'll find the factors, which means you find the zeros along with their multiplicities, and then you have all you need to graph it. What it should look like, if you'd like to have it for your notes, is -3 is a 0, 2 is a 0, and 4 is a 0. And the graph ends up looking roughly like this. Where this this y-intercept is 72. So please try that one at home. It's a good practice of both unit 2.2 material and 2.4 in conjunction. So that's what you should get. But if you have any questions about it over the weekend, feel free to talk to me. But I'd love to start. Oh no, I'm gonna keep that up there. Sorry for a second. And I'd love to get just a little bit of a start on 0.8. Because it's a big section, and I know we've already gone through a lot today. You guys are superstars for getting, like, for sticking around as long as you have. It's hard. It's by no means is this an easy opportunity. Not opportunity, an easy thing to do, sitting for math for 3 hours straight. That's a rough call. But thank you, CSN and NSHE, for making it into a 3-hour class.
What's the Y you said 72?
72, yes. Yes.
That's that's because it's a factored form of the 2x squared minus 10, right?
That's from that.
Okay.
That one right there. Whoop. Wow, that's actually really good. That's like consistent too. It's almost exactly right. Excellent. Okay. Anybody still need it up for a second? Are we all good? All right. So now it's going to seem a little bit left field. Why are we going back to 0.8? Why are we going back to this part of the notes? It has to do with the next thing that we're going to talk about in unit 2. We're going to talk about rational functions, and I've been holding on to talking about rational expressions until now because it wasn't really relevant when we were talking too much about anything else. So now let's talk about those things. Rational expressions. A rational expression is a fraction whose numerator and denominator are polynomials. So instead of just dealing and that's the reason why we are studying it here too, is that it's a new application of polynomials. Now, if we take two polynomials and we divide them together, there's way more that we can do with them. So, for example, we've got 2x plus 50, minus 15 over x squared minus 4. That's a rational expression. Negative 5 over 5x plus 2. X cubed plus 5x minus 7 over x plus 2 times x plus 4. That's a polynomial whose denominator has been factored, but that's still a polynomial. It's just in factored form. And then I also wrote 1/4 because technically speaking, one and 4 are polynomials. Technically speaking, they are polynomials. They're degree 0 polynomials, not very exciting. They don't do much, but they are polynomials. Why would I mention that? What I want to mention here, and this is the thing, I don't want you to be afraid of these things. Since 1/4 is also a rational expression, and we know how fraction stuff works. We talked about it back in 0.7, or yeah, 0.7. We talked about fractional stuff in 0.7. All the rules that we learned there still apply. It's just an abstractification of that. So since fractions are rational expressions, and we know how algebra works on fractions. The same algebra must work on any rational expression. Since fractions are rational expressions, they are. They're not exciting ones. They're just numbers at the end of the day. But we know how that stuff works. We learned about how to add and subtract fractions, how to multiply them, right? Multiplying, we multiply across. We also want to simplify vertically and diagonally when we're multiplying. If we're adding or subtracting, we need to find a common denominator. All that stuff that we learned is still relevant here. And so the point being is, since fractions are rational expressions, and we know that stuff, the same algebra practices must also work on any rational expression. Otherwise, the math wouldn't math, right? Otherwise, the math wouldn't be mathing. We can't have it magically work in one case, but not work in the others. So we already had this. I said it for the cancellation property for fractions originally, but it's also for rational expressions. Let A, B, and C be some quantities. So they could, like, this is the difference. Before I said A, B, and C be some real numbers. Now it's some quantities. So they could include variables, or they could just be constants. Then if you have A over B time, A times C over B times C, these C's can cancel out. And this equals A over B, A times B, or A over B. A over B. Provided C does not equal 0.
That kind of what you were talking about with the quadratic equation,
What do you mean?
when you separated the,
Into two pieces?
yeah.
Kind of, like we're going to be seeing how we can utilize that to break apart fractions, but this is slightly different. But it's still, like, I mean, at the end of the day, the quadratic formula is a formula involving rational expressions. Not rational as in polynomials, but rational as in it's a function over a function. So yes, like all those rules can apply to those situations too. So you notice that I've written provided C doesn't equal 0. I'll talk about that, I think, in the next page. Yeah, the provided C does not equal 0 discussion, because we do need to have that. It's an important thing, and it plays a role in calculus and beyond. So it's important to know the distinction, but we'll get to that. The point being, though, is if you have a factor in the numerator and the same factor in the denominator, we can cancel them, whether they're numbers or expressions that are like variables. You can still cancel them. So to simplify fractions, we must factor the numerator, so num and denom, and cancel common factors vertically. We're just going to do one, and then we'll pick up next time, but I just want to remind us of this fact right now. So to simplify a singular rational expression, you're going to look at it, and as it stands right now, x squared plus 6x plus 6 minus 16 over x squared minus 4. You might be tempted to say, oh, well, I can just cancel the x squareds. But remember, we can't do that. Those are terms. You can't cancel terms vertically, because at the end of the day, division is is inverse multiplication. You can only cancel factors. So we can't cancel terms, so we have to factor this first. And just in the interest of time, this will factor to x plus 8 times x minus 2 divided by x plus 2 times x minus 2. And lo and behold, the x minus 2's cancel, giving us x plus 8 divided by x plus 2. And that is as far as we can go. We can't reduce the 8 and the 2 because they're terms. If it was x times 8 and x times 2, we could reduce it. But right now, they're two separate quantities. So they can't get simplified any further than that. Now, as I said in the thing above, I should technically say provided that x minus 2 doesn't equal 0. I canceled the C here, quote unquote. The C portion was the x minus 2. So technically speaking, I have to say provided x minus 2 doesn't equal 0, but we typically omit that when we're writing these things, okay? That's enough for today. It's been a long day. You guys are superstars. You'll get your exams back on Tuesday. If you have any questions before then, please feel free to email me. Otherwise, you guys have a great rest of your day, great weekend. Avoid the social medias. It's a poison on society. You know the deal. You know the deal. Don't do it. It's bad for you. It's bad for all of us. It's polarizing us. It's not good for us. And have a great weekend. Do something fun.